whatever it is, if it turns out that the radiative contribution is much larger than the experimental, then of course we have something that we should call a puzzle, but it's called a problem. Maybe not correctly, but we'll stick to that name, because then what we need is fine-tuning. If one of these numbers is much bigger than the experimental value, then of course the sum has to cancel.
That's why, like, when it's ln of lambda, we don't care because we consider it as a small contribution. But if it's lambda squared, then it's considered as big. Or like, how is the criterion to decide if it is really big or small?
By being big. I'm sorry, I don't want to. I want to make one of those funny answers, you know, something is considered big when it's much bigger than something else.
But like, what I didn't understand is, we always can consider for a perturbative theory the loop corrections. Sometimes it's proportional to ln of scale, or for Higgs, it's the scale squared. So if it's
oh, it's not so much whether it's a scale. If that bugs you, well, you know, in the case of Higgs disappears. Suppose I got this. It would be equally, well, it would be equally a problem. You like to imagine that the physical scales, you believe that there is physics beyond the standard model and it goes to large scale. This is the underlying prevailing view of modern particle physics, okay? And many people would like even to imagine that we should be allowed to go all the way to M Planck. Therefore, this is huge. Put this to be equal to M Planck, just to understand. Put it at M God. Put it at whatever number that is much bigger than Higgs mass. This is Higgs mass. You know what Higgs mass is, remember? It's 100 GeV. Okay, this is a kind of thing that we should have done in the first lecture. Ask these questions that you ask me in private sometimes, because you help each other when you ask this question. So let's now slow down and just talk about this, because now we are talking about the crux of the matter, the essence, if you wish, or what has been guiding modern particle physics were these questions of naturalness, okay? And I want to attack this, and I invite you that from now on, you do me a favor, you just remember this particular afternoon with some responsibility, that you don't just listen to people who tell you that there is a hierarchy problem. Be sure that you go through those arguments, because there is a tremendous amount of confusion and also repetition of empty statements when you have collective motion, as you know, in any social group, even most crazy things can be repeated, even in science, when you cannot measure them. So once again, if I have this contribution, and by definition I am taking lambda much bigger than MW, I am thinking of new physics which is defined in this manner, then this is large, and therefore I need to fine tune. Now go back to the electron situation, it's good that it's not erased. This is small.
Because of ln?
Of course, yes, yes. And it's proportional to itself. That's another beauty, okay? That's another beauty. It makes it easier, because if this is small, this wants to be small. But yes, you're right, because of being a logarithm. Logarithms are small. We believe that there is a cutoff in Asia. You can tell me, well, if I believe in the infinity, then of course this is also infinite, okay? But then you could say I would worry about this too. But it's crazy to worry about that, to imagine that physics will go on in a simple, naive point field theory. It's hard to imagine when you come to gravity becoming strong at a scale.
But for this case, do we need for that something to call naturalism, or to be always proportional to itself to higher order correction?
That's an interesting question. You see, people are very happy. This is very important, what Nicolas is asking. People are very happy when it happens a la Hoff. Hoff says, ideal situation is when, this was supposed to be 0. In the limit of the parameter being 0, you get more symmetry. This is ideal situation. Then you are protected. Then it has to be proportional to itself, and then you'll always get a logarithm. Okay, you will get a dimensionless quantity. Okay, so we like this ideally, this situation. This is normally what people take as natural. Now here is of course a thing to be careful, because In the case of electron, you know, simply when electron mass go to 0, I get more symmetry, so this is nice. So people sometimes do the following. True. I can say that. If in this limit I get more symmetry, the thing will be protected. But then you ask yourself questions, so why is the electron mass small? Then some people answer, well, because of chiral symmetry. Now this is a lousy argument, okay? Because this is tautology, okay? I'm glad you smile, because this is eating your tail, you know, a snake eating its own tail, because why is there a chiral symmetry? Because the electron mass is small, okay? We will come now to the fundamental issue in particle physics, the use of global symmetries. Okay. This situation you're talking about, that Hoff likes, is when there is actually global symmetry in the limit of coupling going to 0. So let's give some examples. Okay, this is important. For example, if proton doesn't decay, whatever it is, and similar such processes don't take place, then we will see that the baryon number is conserved. If the processes that while the baryon number do not take place, then baryon number is conserved. Now, proton lifetime, so here when it doesn't happen, proton stable, baryon number conservation. Now tau p is bigger than 10 to the 34 years, it turns out. So someone asks you, why is proton so stable? And you say, because of baryon number conservation. Do you agree that this is a lousy argument? It's actually more fundamental that proton is stable than the baryon number is conserved. Because tomorrow, if proton is observed in a deep mine somewhere in Japan, we will say, okay, so good, you see. Or M proton, when it's equal to Mn, you get the isospin SU2 symmetry. Very useful, okay? So if people ask you, why is M proton so similar mass to M, you can say because of isospin symmetry. Actually, I would argue that this is really a lousy way of thinking, that this is more fundamental. I would say the following, when this is equal to that, you get approximate symmetry, approximate. Now, global approximate symmetries are extremely useful, because you can do your bookkeeping. If there is an isospin approximate symmetry, then pions should have a similar mass between them. And maybe, you know, if SU3 chions should be similar to pions, it becomes a nice way of organizing, estimating your calculations. So the global symmetries are extremely useful, even if not exact. This is we now know that baryon number is a pretty good symmetry, and this is useful to us. We can remember it, that practically it's unbroken, but we should never use it backwards. In other words, you should not use to me this symmetry, because otherwise you will predict that M proton is equal to M neutron, but it's not equal to M neutron, okay? So this is very important. Although this is useful to have that you should not be used as a reasoning. I'll tell you why. Suppose now that I find out that theta bar is not proportional to itself, but I still find that this wants to be small radiatively. I will be equally happy. I don't care what is it that makes it small. If it wants to be small, I don't have a problem. Okay, I'll come in a moment. So, I give this as example, by the way. I remember we would have a conference here, and we go with a group of colleagues, and I give you an example. People say, of course, you're right. I even tell them a nice story. In the 50s, Maurice Goldhaber, whom I mentioned a few times, who measured neutrino helicity, a great experimentalist who started this search for baryon number violation, the large water detectors in deep mines that led to neutrino oscillations, okay? He and Reines, another great. They wanted to get funding to look for proton decay. This is very nice. I mentioned maybe this once, but let's repeat it again. So he goes to the funding agency, says, I want to measure proton lifetime. He says, no, but proton is stable. They tell him, why would you waste your time? He says, how do you know? Well, they say barrier number is a good symmetry. That's what I want to measure. But they say, no, it's a good symmetry. Look how long proton lives, okay? Because he knew at that time, he had a limit, which is about 10 to the 18 years from our stability. You and I live roughly 80 years. I hope longer. You don't care now from your bloody far. Let's say on average 80 years, and therefore we can put the limit on proton lifetime, otherwise there will be too much radiation and it would kill us very quickly. So there was already a huge limit, so people forgot how it all started. They said, well, this is strange, so probably there is barrier number conservation. Then they forgot then they said, oh, this is now a fundamental thing. He couldn't get the money to do the experiments, okay? So imagine, okay? And people love this story, but yet the same people the day after send a paper to the archive saying, for example, they want to explain dark matter. Now, how do you get the dark matter? It has to be stable. Dark matter is something that is here today, but you know particles like to decay. So they say, well, because they will assume some symmetry that guarantees. I understand this is the same lousy reasoning. If you want to have a dark matter, just say I have a dark matter. Don't tell me that it's stable because of your symmetry, okay? If it's stable, there will be more symmetry, but not the other way around. This is very important. Don't use the global symmetry for your bookkeeping, but don't use it backwards. Don't do that. This is where everybody almost goes wrong. You see this, and then all of a sudden you go backwards and say, I'm making a prediction. Proton cannot decay. That's a point in the parameter space of exact, and there is nothing fundamental to it. More precisely, if you wish, look here. Once you know this, I cannot overemphasize this, okay? Please pay attention here. What that Hoff taught us, and this is very fundamental, since the Fermi mass is always proportional to itself, any number is as good as any other because contribution will always be small. Doesn't matter what this is. In the standard model, remember the scale is 100 GeV roughly. It could be top quark, whose mass is 100 GeV, or bottom quark, 5 GeV, or electron. They are equally protected, or 0. But 0 is not a special point, okay? This is very important. Any point is as good as any other. So to make a prediction because of symmetry, say, I want my mass to be 0, it's like, of course, if you assume that it's 0, you will get some consequences. But you could also take it to be 2 GeV and say, I now have a prediction. From there on, I will get some consequences, okay? That's not good reasoning. Okay, I cannot overemphasize. In the case of, you will see why it's related to what I'm talking about. Global symmetry, 0 is not a special point. However, there are situations when it is. Gauge symmetries. Remember what I taught you, what we studied a lot? If I take the W mass is non-zero, no matter how small, the theory doesn't work. We had to introduce spontaneous symmetry breaking. We couldn't take W to be massive. And later on we calculated Higgs decays into 2W, unless it goes through spontaneous symmetry breaking. We found divergence is why, because for example you can look at the propagator, right? Or the polarization states, and there was this thing. This diverges. This is a special point. So when what does it mean? There is no theory with explicitly broken gauge invariance, or global invariance for that matter. For example, in QED, the global invariance, the conservation of charge, is a special point because you cannot formulate QED if charge is broken. We don't know how to formulate that. We simply cannot. So that is then a real prediction. So in other words, when the fathers of the standard model tell you what happens in ultracurrents or whatever else they tell you, these are actual predictions because they have to be at the point. But not in this case. This is tautology. Okay, that's very important. Now what I want to do, I forgot to say here, Mahmoud asked me, this theta, remember in QCD, remember first there is no CP violation, so theta will never get renormalized. If there was no this thing, if you put theta to 0, it will stay 0. Also, it cannot be a perturbative term. It's a surfer thing. Imagine it's a thing at the infinity. You're never going to generate that in perturbation theory. Okay, this is actually very strange. What we've learned that this somehow knows about what happens at infinity. This was the divergence of a current, and yet it didn't vanish at infinity. There is something strange happening here. What is important? It will never be induced. If you set theta equal to 0, it stays 0. But this, we have to check. This we can do the usual perturbative calculations in.
I have another question.
Please.
This, because, for example, the neutron, from the strong interactions standpoint, we don't use perturbative methods, and maybe we should not talk about quarks independently. So, if
Sorry,
like we are below the lambda QCD, or like we are out of the range of perturbative calculations for strong interactions.
Oh, the way I estimated the electric dipole moment, right? This was not fair. I agree with you. Then I said, forget it. Simply forget it. All I meant to say, dimensionally something like that will happen because that's not how you do it. You use lattice calculation. You do this MIT bag model. MIT bag model is like a shopping bag that somehow you take into account the confinement of the things, and then you do the non-perturbative. These days it's done on a computer, right? It's a simulation. So.
But my question,
You're right.
My question is about, can we also use the weak perturbative calculations regarding the U and the quarks inside the neutron, if they are not
Well, that's what you're saying. How do you address when you calculate the quark? You're asking me what is the connection between the quark and the bound state. But we had this problem already. Remember when I calculate k long, k short? We already faced that. And I had no idea how to do it. I cheated there, okay? I know more or less what they do. We pretended that these are quarks. And so we got, who remembers? S bar gamma mu. Well, I can even write S bar gamma mu dl. There was twice square. Delta S equal to, so SB, SB. Then remember this is order 1 over mw squared. So there is g squared over aw squared. Then there is another g squared, there are g to the 4th. And then there was, remember, the smallness of the, I will, it's good that I write it here, you will see in the moment. Something like this we got, right? The usual electroweak contribution, plus the loop, so there was another probably 16 pi squared, because this is a loop. And what does this mean? I have to now put this between k and k bar. You see, and this is the art of trying to understand strong interaction. Is the art of.
So the form factors can be.
It's sort of, if you wish, it's even more than the form factor. Form factor would be something. Form factor we had, even if the proton was some kind of pudding, some kind of jelly, there would be a form factor. But now this is even trickier, right? You have these isolated quarks and gluons. And this is why we have no idea how to do these computations. Why to this day QCD remains a challenge. There is a prize. If you can do anything analytically, you will get a major prize. So, and then I used dimensional arguments here. I knew that the dimension had to be, and I actually was wrong. At some point I said this should be order mk cube. It has to be cubic because this has a dimensional mass. But actually it's not true. It's fk squared times mk, where fk is the decay constant and so on. But it's not so different from mk. It wasn't so important for us. But yes, you're right. This is very complicated. So as more sophisticated the calculations get, the limit becomes more and more sound. It's cited by everybody 10 to the minus 10 as a rigorous number. Experimentally, theta bar is less than 10 to the minus 10. I shouldn't even say electric double. You know, how do you... I try to make it easier for you. You should say, forget, don't even tell me how you got it, because it's some magic. What we have to estimate in order to know. Now look where already you can see that this is a little too naive. Do you remember when we studied BCKM? We had 3 angles and the phase delta. You remember that if you put one of the angles to 0, phase disappears? I can eliminate it. This is something you have to remember for forever. One thing only about BCKM, I took the pain, I know it's easy to forget, I took the pain to look at this stupid big matrix, which is not... after all, you know, I associate the phase delta with one of the mixing angles, let's say theta 3, put it. The other phases we could get rid of by judicious choices of quark phases. But then take that angle to be 0, there will be no phase. Since there is a symmetry between these angles, this must be true. So we found out that with other angles we could just, you know, it was an oral thing. We could change a row and a column, if you remember. It was boring, but we could do that. So in other words, if any of the angles, it's enough that theta I is 0 and the phase doesn't exist, which has to be obvious physically, because phase is only one associated with one of these 3 Euler rotations, which means that the CP violation that you would expect naively would be theta 1, theta 2, theta 3 times delta. Signs of the, you know, they are small, so I take, right? It must vanish, CP violation, when any of this quantity goes to 0. This is about 10 to the minus 3, this is about 10 to the minus 2, and this is order 1. Actually, a little more. Anyway, the number is some number about 10 to the minus 5, 10 to the minus 6. It's not 10 to the minus 3. So why CP violation now, we can ask, so big? Do you remember why it was? This was the CP conserving part of K long, K short. This was purely real, because with 2 generations there are no phases, obviously. Well, it's even 1 angle going to 0 is enough, but here we had 2. So this goes as this, whereas the CP violating piece will go as mt squared over mw squared times this small mixing angle. So notice there is an enhancement. There is, of course, the smallness of this mixing angle. But I get also an enhancement, m charm over mt squawk is very large. So, a priori, you and I don't know how this will go. This could be even proportional to this whole thing. It could be maybe 10 to the 5, 10 to the minus 6. Now already it's not so big. See, we have to be careful. So let's do the calculation, if you bear with me. When did I start? Did you pay attention? Quarter 2?
Yeah, quarter 2.
Quarter 2 I started. So, sorry?
The recording.
Is it recording the class is being recorded? The class is being recorded?
Yeah, the class is being recorded. No, that's okay. I don't know when I started. Half an hour ago? Is it possible? I forgot to time you. I want to be... you think it was 15 too?
Yeah.
Okay. Okay, you look, half an hour. So that means another 45 minutes. Slow me down. So now let's look at the argument determinant term. Once again, this is not renormalized. I don't have to worry about this. If it is 0, it stays 0. But this, I suspect, may not be as large as naive argument goes. Okay. So this is a work of Ellis and Gaillard in 1979.
You say that theta is not normalizable? It doesn't
Theta, it's not normalizable. You see, it's not it cannot be a perturbative calculation. It's a surface term. If something happens in the field, you will never get this in perturbations here. Also, you can think about that in QCD. If you just think of as physics, if I set it to 0, there is CP violation. Therefore, CP violation guarantees me that whatever I confuse will be CP conserving, because in CP conserving theory, all the predictions are CP conserving. Therefore, theta would be proportional to itself. Okay? Even if it gets renormalized by whatever, it will be proportional to itself. I don't have to worry about that. What I have to worry is this. There is no reason they should be proportional to itself because CP is violated. There is no CP argument. Okay, so let's do that. We have to do the perturbation. I'm going to work in the physical basis. What it means that quark mass is diagonal. I perform that rotation. This is why I have argument determinant m. And the only CP violating things is VCKM, which I call V, which is complex and unitary. And, you know, I have to look at the corrections of this type. A left-handed quark. Remember, the mass term is the thing that connects left with right. And we typically denote it like this. Mass insertion. When I, by this, I mean MQ, Q bar Q is MQ, QL bar QR plus commission conjugate. And we denote it like this. It just says that I'm going through the mass term. Just a picturesque way of saying it. Then I have here W. So these are typically the diagrams that I have to compute. One loop connection, imagine that if I'm in a 2-loop connection, it will be like this. And if it's a 3-loop connection, it will be like this. And if it's 55-loop connections, I don't know. So this is our theta bar. Now, how do I do it? Okay, I have to do the thing. I have to remind you, remember that if I have a determinant of some e to the m, I'm interested only in non-singular matrices that can be diagonalized, like my quark mass matrices. So what is this? This is em1, em2, and so on. So this is e to the trace m. This is a famous relation for non-singular matrices. In other words, determinant m is e to the trace logarithm m. Okay, the first expression that we need. Okay, I want to compute, what am I computing? Argument determinant m. Remember, I have to start with determinant m. Now m is m0, the tree level. Remember, the quark masses are proportional to themselves. You can see here. Notice that I can change left to right only here because W couples only to left-handed quarks. If I change it here, I have to change it again because W cannot couple to a right-handed quark. This is to say, the mass will always be proportional to itself. In other words, m is m0, 1 plus something that let me call epsilon. This is a matrix. This is the famous chiral symmetry argument. This simplifies my life to do the calculation, right? This is loop. So what does it mean? That trace logarithm m is trace logarithm m0 plus epsilon. I'm going to expand it. I'm doing perturbation theory, so epsilon is small. All the elements of epsilons are much smaller than the 1. Okay, you will see that it's very justified. I will get something really small. So if I say at 1 loop is it so small, it will be even smaller than the 1 loop. So the elements notice argument, determinant m, is, I have two pieces, is argument, determinant, e to the trace log m0 plus epsilon. No determinant. Well, I don't know what is the argument of this thing. I can't compute that, you see. I don't know what it is. What I'm interested in, what is the loop contribution? In other words, I want to know what is the complexity, how much theta bar I will get from the loop. Remember, I just want to do the loop. So I can as well say, okay, I will normalize the travel. Let me take M0 to be real. I'm asking the following question. A Hoff kind of question. If I assume that theta bar is very small, that argument determinant M0 is 0, what will I get from the loop? So let's take this to be 0, this argument of this. Let's assume M0 real, therefore we will get that this is imaginary trace epsilon. The argument of this thing is just imaginary of this because I get e to the trace epsilon in perturbation theory. So I'm doing this loop. Okay, how shall I call it loop? This is what I want to do. This is the first step that Ellis and Gaillard realized. In 79. It's amazing that how old the paper is and it's being ignored to this day. When people speak about the strong CP problem, those that know never want to cite this paper because if you cite this paper then you cannot argue that there is a problem. So it's sort of one of those sad things that they get much less citations than they deserve. Oh, I should have maybe erased this. But instead of the, oh no, I shouldn't. Let's keep it just to see. Look at this diagram like this. I have to take the trace of epsilon. Now notice that this thing here, if this is V dagger. Do you see it? So let's be clear. UL comes in, DL comes out, DL, UL. If this, well, let's call this V, this is V there, by definition. V was the mass matrix was the standard model. We wrote UL bar, gamma mu, V, DL, W V plus, G over square root of 2. This is the definition of ECKM. If this is V dagger. I need to do this carefully and slowly. Notice that there is a conspiracy. You can start smelling it. It's not going to be easy to get something imaginary. This argument that you expect the loop to be of order 10 to the minus 3 is a lousy argument of a thoughtless person who didn't even look at this. Because this thing now, it's because when I have V, I get V dagger. That's not, the trace of this is 1. But you say, wait. When I do this here, you know, I have a propagator, which is IP slash plus n, t square minus m squared. So I can have all kinds of higher powers of m if I would think of expanding it, okay? What we do that, we say, this is how they do it, and it's very nice. They say, well, it could be happen that I go through the mass here, so it becomes dr. But then I must go again through the mass, because only only L interacts with the W. This is W. Remember, W is the only source. This is a beautiful property of the standard model. Everybody else considers CP. Higgs, Z boson, photon, they consider CP. W is the only source. So they are saying, I don't even know how ugly this calculation is. But unless I put some mass insertions here, I will get 0. The beauty of their reasoning is they don't have to compute anything. They can just reason out. So look, trace of V. This here, whatever power I would call, let's say MB, and it has to be even number of times, which is not so important at this point, but let's put it to 2n V dagger. Do you notice that this is 0? I'm in the physical basis where m quark is diagonal and real. Positive number. The mass of a quark is 2 MeV, whatever. Right? Because the trace is cyclic.
So we insert those mass points an even number of times.
It has to be even number of times, otherwise you will not interact with W. That means you are getting some contribution from the loop, which is proportional to the mass to some power.
So that every time I put that thing, I introduce an MD.
Right,
Okay.
right. And if, of course, if you're looking at the up quark mass down quark, then you will be M up. Okay. So now that means that at one loop level you will get nothing. Now look at the comparison, it's interesting. So you say, so what about this kind of diagrams? There is this always external when you are going to UR. We are looking at this was the zero, so the mass matrix that I said, I don't know what it is. I will assume that it's small. I want to know how stable it is, okay? I'm looking at I said when I have some physical parameter theta, it's theta 3 plus theta loop. And I want to see how big theta loop is in order to know what is going on. Okay? I don't care what theta 3 is. Now, let's do this. Let's do this 2 loop. Where did I? Where should I put it? VCKM is V. Let's put this. So at one loop level, I get 0. This is 0, right? At the 2 loop level, 2 loop. Or more loops, I will have imaginary, trace. I start with V here. Then I can put some power of let's start with up quark. Well, let me write for simplicity. I'll think about dimensions later. And U, 2 and 1. Remember, it has to be real, even. Then there will be V dagger. When you put V dagger, so if this was an up quark, then I'm gonna get V dagger here. Let's say this was an up quark, so V, so this was a down quark. Okay, MD 2n minus 1. Now this must be D going to up, it will be V dagger. Now I can put M up to 2n 2. Bless. Actually, I could have put some extra. I forgot to do that. You told me, why don't you put some extra? This is also 0. This may not be so trivial to see. But let's do it before we. okay, before I write things down, what I did here at the one loop level, because you have said, well, put some external insertion. I don't care, make it. One loop tells me that when there is V, there is V there. But do it as the worst possible thing. I want to get it the most probably complex. Who sees that this is real or it's not real? First thing that I remind you, that trace of X dagger is trace of X star. Do we agree with this? By definition. V dagger has elements which are complex conjugates. Well, they inverse them, but on the diagonal it's just. So let me call this X. So trace X dagger, what is trace of X dagger? Help me. Is mu is trace mu 2p. Now I need you to follow me. V md 21n V dagger. Correct? Now I can write it as a trace of, I can put V first. V md 2n V dagger mu 2p. I'm using the cyclic property of the trace. So I'm finding out the trace of X dagger, which is trace of X star, is equal to trace of X. This is trace of X star, but this is equal to trace of X. So it's real. I forgot to do that. I took sort of, I cheated here. I took as simple as possible situation.
I don't understand why we can insert that. We go.
Oh, I don't know if I can, I don't even want to worry. You were saying you don't want to, maybe I can insert twice here, outside. It looks ugly, inserting it on the outside.
Yeah.
It doesn't matter. It wouldn't show up in the correct. But you can say maybe that you know what you could do. You could insert a gluon, and gluon doesn't change chirality. You can do whatever it's just a way of saying that I want to be as ignorant as possible. Maybe through the Higgs or through the gluon, or even if I put it. Okay, I agree with you. I don't see it immediately. But even if I put it, it doesn't change anything.
The mass here is the renormalized parameter for UNT.
This is a physical parameter that I put. I'm in the physical basis. I'm just calculating the phase of that thing.
So MD and MU are real.
Of course, real and positive numbers. The only source of CP violation in the physical basis is this is how standard model. You can also work in the other basis.
Okay, but my confusion is
we will get the same answer.
we define the propagator, the mass in the propagator is the whole of the whole loop calculations. We end up at a physical mass which includes all the contributions from it. So if you are looking for an imaginary part of mass parameter coming from the loop,
I'm looking at the imaginary part of the argument determinant M. It's not the, I don't know what, I'm looking at this, where I'm propagating real physical particles in the loop.
okay,
This is a 3-level quark mass.
the mass that we put.
Of course, this is a 3-level quark mass. I'm just doing the loop correction to that. I cannot now say that this is also, I can always redo this when I go to other loops. But I can just work with the 3-level masses and then put everything in V and then compute the loops with that precision. That should be equivalent to what you're saying. We should be equivalent to working also in the original basis. It must be. It will show up differently, but it will show up. There is no way that you will get anything without V, right? There is no way you and I can produce CP violation without V. There is no complexity in the quark mass. If V was real, that everything would always remain real. This is the argument of the chiral symmetry kind of argument. There is a symmetry which is protected. and this is CP violation, and that's the phase of V. So everything in the end must boil down to the phase of V. So the thing is, then the first possible configuration, the next one, when I have 4 V's, imaginary trace V, MD, 2N, V dagger, MU. Why don't I try with 2M? Oh no, it's M. Okay, I, J, V. I don't even now worry where it's coming. We can now find the loops later. But I want to show you what is the minimum that I have to have. And this is V now, so this will be MD again, 2K, V dagger, MU to 2L. I want to have 4 V's and I put as much mass insertion any which way I can. So maybe one loop will come from the gluon because I don't want to put more W's, okay, because I want to put these mass insertions, okay, so I may have an extra gauge boson, so that it's not just on the leg, but I have some kind of gluon here, which doesn't change chiral, so I put it here. So this is my, now this is X. X. So once again, trace of X dagger. Okay, I don't know if you want to bear. Shall I just cite the result or shall we try to see it? Let's try to see it just for a minute. X dagger would be trace of MU to L, V, MD to K, V dagger, MU to J, V, MD to I, V dagger. I think this is correct. So I can move this there, okay? Notice what I have. I have interchange K and I. Okay? Do you see? So, and I need the trace of X dagger is different from trace X, otherwise it's real. Therefore, I must be different from K. And you can play with some more rotations, you will find out that J must be different from L because there is no difference between up and down. Everything is completely symmetric. By the same argument, once again, this trace of X dagger must be different from trace X, but it is equal if K is equal to I. So I must be different from K and J must be different from L. It's not easy to dig that out. The paper is sort of hard to read and there is a lot of stuff in that, okay? I'm trying to simplify it as much as possible. So if you can follow this, it will be useful for you.
Should be different because we know it should be imaginary. Because we know there is CP like that.
No. The fact that there is, the only thing that I know that V is complex. All I'm saying, I don't even know whether this is true. The only way that I can get, I'm trying to look the first possible loop contribution to theta bar. Theta bar is argument determinant M. I said at 3 level I just set it to 0, I don't care. Or I look at the difference. I'm looking at the radiated correction. In order that this is non-zero, I must have this. This still doesn't guarantee that this happens. Maybe there are some cancellations. People did sit down. It was first them and they made some mistakes and then Kriplovich and some other people actually did and found that at the 3-loop level this actually does happen. This is just showing you that this must happen in order to be non-vanishing. Whether or not that happens, you and I have to evaluate this 3-loop. We won't do that. Why we won't do that? Look. Why we won't do that? That tells you that my theta bar loop standard model must be at least 2 loops. Actually, they say it's. I'll be as conservative as possible. So I'll put this. It means that the down quark mass, if I want to put as small numbers, as small dimension of I, j, and k, because it's a dimensionless quantity, so every time when I have n quark, I divide it over mw, which I didn't write here, to simplify mine and your life. So if I will take, in other words, I will take I equal 1, k equal 2, j equal 1, L equal 2. This is the minimum. I is different from k, so if I is 1, k is 2. If j 1, L is 2. So in other words, notice I have a down quark mass twice and 4 times. That's 6. The heaviest quark, I don't even know whether I will get it. But this is at most I can get. M top I will over mw is 1. So there is no suppression. And then there is at least this epsilon CP violation. Actually, I suspect that there should be theta 1, theta 2, theta 3, delta, but I want to be cavalier. How big is this? This is 10 to the minus 4. MB over mw is 1 over 20, roughly. 480. 1 over 20 to 6 power is 10 to the 8. Epsilon CP violation is 10 to the minus 3. And this is sort of really being as conservative as I can. So I got this minus less than 10 to the minus 15. Not only it's not 10 to the minus 3, it's always a magnitude smaller than the experimental limit. This is why I cannot overemphasize this. There is absolutely no strong CP problem in the standard model.
So people when able to say that thing will be just
Right.
epsilon CP
Right.
without computing.
People that speak now of that, they don't cite Ellis and Gaillard. Well, there are things to think about, okay? We can keep on talking. I'm about to finish. No. Yes. No. Yes. Wait, when did I start? Well, I have another 15 minutes, right?
Yeah.
We can do it nicely in 15 minutes, okay? Let me see you. Let's get another shot of energy now because we are getting there. Oh, but you can tell me. Well, this is the finite contribution, but maybe there is an infinity in principle. True. Now notice. This is a little delicate, but maybe you can follow it with your little knowledge of field theory or normalizability. What does it mean when I put mass insertion? When I have a diagram like this is superficially divergent, as you know. You get the logarithm, okay? But when I put extra mass insertions, I'm actually making it more finite. You should think like this. I have a propagator which is p slash plus n. And then I'm saying I'm going through m. This is what immersion is. Sometimes the diagram goes through p slash, sometimes it goes through m. If it goes through m, it goes like this. If I go through m twice, I'm making the diagram extremely convergent because it's not now 1 over p. It's 1 over p squared times 1 over p squared. Therefore, because of so many masses that you have to put, 6 plus 6, 12, you could convince yourself, every time I bring 2 mass insertion, I have to add another loop. to make it divergent, because at one loop level this is extremely convergent. In other words, this is the same paper Ellis and Gaillard. There is theta bar infinite loop, okay, infinite, quote unquote, which will have the same form, because it always has to have the form that I calculated, but you need alpha over pi, 6 loops, because you have 12 powers of mass we had. Each time I bring another loop, n bottom over nw to the 6, epsilon CP violation, logarithm lambda over something, maybe mw, the scale of weak interactions. It doesn't matter. This is 0. This is even more protected than the electron mass. This is crazily protected. Look at this. This is 10 to the minus 12, 10 to the minus 2 to the 6 powers, 10 to the minus 12, 10 to the minus 8 is already 10 to the minus 20, then this is 10 to the minus 3 times logarithm lambda over whatever. So take any cutoff in the world. This is a number whether 10 or 100 or 1,000. You have to take lambda, I don't know, astronomically. So if you take Planck scale, you will get here roughly 100, I think, 20, whatever. So notice we get a ridiculously small number. Theta bar, is this a hint? Is nature telling us something? I'm not sure. I will now wrap it up and try to tell you why people worried about the strong CP problem, because people started to worry in 1977 when people realized that there was this, in the mid 70s to 77, people realized this instant-on picture, theta bar and so on, and then lazily everybody said this will be large. So in 77 and 78, various solutions were offered to a problem that didn't exist. There is something interesting about the so-called solutions to the so-called problem, and it's worth discussing that. After we conclude, you and I, that there is no problem whatsoever, because I just show you, I don't know what theta is. I don't know what argument determinant M0 is. All I know is the argument determinant M from radiative is much less than 10 to the minus 15. Actually, they claim that they got 10 to the minus 19 when they put the numbers. One reason can be easily that this is actually not 10 to the minus 3, but you get a Wolf suppression there. There is no reason why you would have this silly thing. The reason, remember, that CP violation is so big in the standard model, it's not small, it's big, because top is very heavy. And it's not just this suppression angles, okay? You may still ask me, well, I am very ambitious, I want to know why this is small. Okay? Be careful when you ask such a question, because...
So,
yes,
when we talk about naturalist problem, I think you say that through Hoff's definition, if we have smaller loop corrections, then we don't worry about naturalness.
Absolutely not.
Without taking into account what the initial value is. It can be small, it can be large, but every contribution, if it's proportional to the first, then we are okay.
No, when that happens, this is one of the ways. One of the ways is you get extra symmetry and you get something proportional to the original number, that's for sure. Here there is no extra symmetry. Here this is not proportional to the original one. I actually generated at the loop level. Even if I take this to be 0, they claim that you will generate something here, which I didn't prove that, I'm just saying it could happen. They computed, they got 10 to the minus 19. It's still protected. Structurally, this is interesting. The standard model has an inbuilt structure. The way it goes, the CP violation, the way it goes that V is the only source, and every time there is V dagger, actually wants to protect this theta bar term.
So we don't need to introduce any extra symmetry. It's
absolutely not, because you see, what would the introducing symmetries be? You are saying I will introduce a symmetry to make theta small, but then I ask you, well, why did you introduce that symmetry? When you introduce a symmetry, you will have to put some terms. Well, we'll talk about it tomorrow.
And
Not today.
why did we throw away the 10 to the minus 3 that is determined by...
No, we didn't. I said this was someone said, I don't know who or she was, look, the CP violation, the standard model is all the 10 to the minus 3, so I expect this to be all the 10 to the minus
So
3.
this is a number that experimentally measured, or?
No, epsilon CP is the CP violation that has been observed.
Okay, so...
Nothing to do here. The only thing that was observed, there is a limit. This is experimental limit. But people said, I would expect this at the loops to know about CP violation of the standard model, so I expect this to be 10 to the minus 3.
So then we have the opportunity to share how much contribution each term gives to have a theta bar which is smaller than 10 to the minus 10. And we say that even in the case that our determinant of n is 0 at the 3 level, corrections are small.
They are much smaller than the experimental bound. This is an extremely well protected quantity. I know of no quantity that is so well protected.
But in any case, we need to fine tune somehow the theta to give the theta bar, which is small.
No fine tuning. No, fine tuning is a cancellation of two large numbers. Fine tuning would exist. Now this is different. Fine tuning means if I get, look, I got this 10 to the minus 19, let me write it down, which is my theta bar. So, fine tuning means that if I get a large radiative correction, then the 3 level must be large and it must be cancelled, but I got a very small radiative correction, so there is no fine tuning whatsoever. It's opposite from fine tuning. This is extremely stable. Whatever it is, it wants to stay what it is. You cannot change this radiative. That's what Alice Kayar taught us. Extremely surprising result. It came as a shock to me. I mean, a year before they wrote the paper, with Mohapatra, we wrote one of the first solutions to the strong CP problem.
I can make a question.
Please.
Why is so well protected?
I don't know. Well, because of that stupid calculation. I didn't give you a nice, elegant, simple reason like the Carl symmetry in case of electron. I agree. It's just the structure of the standard model. It's a strange thing how V and V dagger go together. And the number of mass insertion. And the fact is, if I ask you, why did the K long, K short work so well? I can't give you an answer because Chang quark has to be light. And this is very important where people get confused. And I think this is a problem of teaching. We used to discuss it a lot with Boris Goldhaber when he was my colleague at Brookhaven that there is, if I teach you, as most of the books do, that the G mechanism automatically solves the K long, the size of the K long, K short, the flavor conservation in ultra currents, it's very, delta and K is very small. You should ask me, remember delta and K over MK is something like 10 to the minus 14, 15. Why is it so small? There are a number of things. When I went to compute it, first there was a loop. Then there was Cabibbo mixing. Then there was another G square. Then MW is much bigger than MK. Then I found out that M charm entered. And M charm has to be 100 times lighter than W in order for it to work. So when you ask me why, now you tell me, well, because charm is light, but then you ask me why is charm light and so on. It's like, when children ask you, why. I used to do that with my daughter, why, and then it goes on forever. It's somehow, good theories work dangerously. There is a way of teaching and a way of thinking, a way of which has pervaded the field, to think that your theory should work for the whole parameter space. No, the standard model works miraculously in one point of parameter space. First, M charm In order for to be M charm has to be practically 1 GeV, which is much smaller than MW. I remember I mentioned this some years later with Marciano at Brookhaven. We computed something in SUSY unification. I can tell you about that if I teach you SUSY, if you want to hear something, the connection to the Higgs mass. And we found out that in order to work, M top should be around 200 GeV. I mean, everybody told me, no, this is impossible. Look, you're crazy, because then theta 1,3 mixing angle must be very small, otherwise you get too much K long, K short. You see immediately it has to be 10 to the minus 3. Remember, top quark enters with theta 1 minus 3. They said, no, but that's ugly. Why should be? you ask me. The point is that the good theories work in a point of parameter space. Something divine makes it work. There is a divine conspiracy to make you not worry. But you are saying, I want two things that you could say. I still want to understand. And I will then invite you tomorrow to think together with me. Can we ever do that? What would that mean to understand that? But I want to know why theta is small. Or I want to know why argument determinant M0 is so small. Okay, you convince me that there is no problem, but I'm more ambitious. We can address that. You can also ask maybe a nicer question. How is it that this surface term contributes physically at the end, this crazy thing of theta? Shouldn't there be a messenger for that? If you like to think that there should be someone who knows about this infinity, you can fall in love with what is called the axial solution to the strong Peccei-Quinn. It's not a solution because there is no problem, people are wrong. In order for it to work, to explain why theta is small, Peccei-Quinn has to assume that some other parameters are very small. At the end, it will always be like that. What is nice, I'll show you, that there is a beautiful dynamics. This axion is a real field which sort of knows about this strange QCD structure and so on. Okay, that is always nice. Having a dynamical picture when you had a static parameter, it's always nice. It turns out that this guy could be the dark matter. That's very nice. It could even be there could even be a way of, well, why am I anticipating myself? Let me go on. If you find this interesting, I'll go on until I see that I'm boring you, or so that I can tell you some other things. But surely tomorrow tomorrow we would have to recapture the essence, because there was a lot of material today. We must have been very, very fast to grasp all of this. I'll spend at least 15 minutes tomorrow reminding you what I had to make you assume. You see, I did this calculation. You see how I chose. I did a calculation because you and I know how to do perturbative calculation. I skipped those technical things that would take us forever to learn. I stopped here. I wish there was a blackboard. It's not good when the blackboard is small. I was actually in Greece. It's sort of terrible. There was a whiteboard. I hate whiteboards. And it was very small. And you don't think of the lecture hall blackboard. When you see that you have, you start being more organized. You write. You know that you don't have to. Why is it? Who did this? It makes me angry.
Because of
Oh, but that could have been put somewhere else. No, wait a minute. That's not a good. I mean, it was there already. This came before, and it was okay.
maybe they could.
They can link
could
the
put the-
We could have at least those things that. It's not as nice as our ICTP platform. Salam did a great thing. ICTP is a great thing. But there were three great things we always said. That we had great vision, Salam. One was to have a good bar, a beautiful bar. One were directors went crazy, wanted to get rid of that bar. Remember, I was away, I came back, there was a war. I went to war to save the bar. I don't know if you understand how much bar is important. Also, there was a time where books were important. Maybe you don't know this. But we actually would go to the library and read books, we didn't. This was the best library, ICTP in the world, physics library, probably. So Sanam had this great vision, okay, and a great blackboard. The ICTP lecture board blackboard is the best blackboard I used to love to lecture here in the 80s because I just, if you were organized, you could time yourself. In 1 hour and 15 minutes, you could, that was a summer school, you could stay on your own blackboard. And it really helps a lot. It's amazing because you're not there because you don't remember what the speaker said, right? You go lecture, so you go back, it's there written, so you can continue thinking without having to ask all the time.
How could it change this computation if we accept it right, W, false?
Oh, that's a good question. By the way, you will see one of the solutions that, well, first Axiom came, and then immediately after, Mohapatra and I and Howard Georgia separately came with this possibility that you see, this beautiful question that you asked, for the following reason. And it seemed that we had actually a beautiful solution to this problem that it's not there. Like this. In a left-right symmetric theory, there is parity. And I'm not introducing for this. You have to accept it if you want to understand the dynamical origin of chirality of weak interactions. Therefore, our argument was, look, but parity sets theta equal to 0. Parity tells you why theta is 0. I don't like this argument anymore. Because the value of theta tells me how good parity is. Am I really helping you understand that this has to be 0? You can tell me no. If theta is non-zero, your theory is not good enough. So I would now say I can have a consistent scenario, but I'm actually confusing you. I confuse myself. When it was amazing, I told you, the whole week. It was 6 hours of lecturing, and then we would go for lunch and dinner with Vali and this group in Munich. They had thought about the strong CP as obsessed as me. I was attacking axions, he was attacking, it was sort of, we finally converged, and we now agree that this, but at least I can be consistent. Also, argue with determinant M can be real because M was Hermitian. The left-right symmetry in principle give me a chance. There was this is what I should tell you, okay, it's a good question. Really good question. I can have a consistent picture of a small theta. But then, even the standard model is consistent because when I tell you that, you see, people sort of get, this symmetry makes you forget what is more important. So you tell people in the standard model, theta is 0. They say, no, why? Then you tell them, look, but in this theory there is parity. It's a cheat. It's not really explaining why theta is small. It's the value of theta will tell us how good the idea of left-right symmetry is. I'm consistently be small, but so is the standard model. I claim nobody can do better than the standard model. Let nobody fool you. You cannot do better because in order to have something, Peche, Queen, left, right, you will have to impose something on your theory. That means you will have to make some couplings be 0, those that violate what you like to have. That's equivalent to saying that theta is small. Instead of saying that this is small, you will have to say that something else is small. And this is not a special point. Remember, this is not a gauge symmetry. The only way to have it, and I'll tell you about that if you have a gauge symmetry, that naturally leads to that. I've worked a lot on this and I myself fail. And everybody else, in my opinion. It was very strange that I studied a week. We were very excited about this, and I'll be actually lecturing on this. I have some lectures in the States in the summer and the early fall. We started a fight with Vali and company in Munich. He attacking my left-right symmetry. Now at the end of the, he called me, he likes this much more. I managed to convince him and he managed to convince me. I started attacking axion, I think I like axion more. when I did before, and he calls me, he says, I like this, so it's funny. It's very confusing, and I want you really to appreciate this, that here, when we work on this, we have to worry about the logic more than about the calculation, because there is no real problem. When there is a real problem, notice, you will have 5 months later or 2 days later, someone will come up and solve the problem in consistency. It's always, there is a genius who solved that problem, or you find out it was solved. When you keep speaking for 30, 40 years, that means there was no problem. So therefore you and I, have to understand the logic of what you are doing, in order not to waste our energies on what may not be the right thing to work. Okay. It's enough for today. Questions? No.
I was wondering why we didn't work the Higgs, because it's give less contribution.
Oh, the Higgs.
Right?
The Higgs is real, the couplings of the Higgs.
Okay, so it gives just real.
You cannot contribute to the imaginary part. Higgs is like the photon or the Z boson. This is interesting because he could have done something directly. Higgs check helicity from L to right, he can help you. Higgs is responsible for the masses. No, that's important what you are asking. But it's real, the couplings. And I'm working in the physical basis where M quark is real. I insist on that basis. I'm not going to change that basis. And I will keep M quark real. When I do my perturbation theory, you understand that one loop you also keep your quarks masses real. You renormalize them, but you keep them real. The physical quantity that we call M quark is real by definition. Positive, it's a number.
I have a question about that. Maybe I didn't understand very well. To clarify that, for this relation, theta bar equals theta plus arc determinant mass matrix. We don't have any idea how big theta or argument determinant and how big that.
No, we have no idea, you're right.
Even through the CP violating complex space, I can't argue how big arc determinant n is, right?
How can you know at the tree level? You see, it doesn't enter into the only thing that enters was, remember what entered was Kobayashi Maskawa is UL dagger. This quantity simply never enters. Let me remind you, this is very important, VCKM, UL up dagger, UL down.
It only enters here.
Whereas argument, determinant, and Q, just to appreciate it, is argument, determinant, this is really what entered. How did the thing appear? It appeared because I performed chiral rotations. So the thing here has to do with the difference between left and right. CKM doesn't give a damn about right, or the difference between left and right. It only knows about left. Therefore, this quantity here it cannot be answered in the standard model. That's why the question that Nicolas asked is once you have a theory beyond the standard model, you can go and ask that question, and you have to be consistent. I don't think I can ever tell you why something is small without taking in something, but at least I can try to be consistent, because there, however, both left and right enter, and maybe this is why you ask. Because of WR, there is UR, and there are loops because of WR, where UR enters. So therefore, this quantity now becomes a physical quantity, and you can study it. But not in the standard model. Nothing that happens in the right-hand sector, and this is why we keep eliminating phases. Remember when we counted the phases, there were 6 phases in the standard model, but we kept changing the phases of left and right quarks, they never entered. For example, if you had a left-right symmetric theory, then if I make the VCKM real, the right-handed one will not be real, because you are making different rotations there. And therefore you will get another origin of CP violation that you have to worry about, not in the standard model. This is why standard model, the same thing. It's amazing. I'll try to recapture this for you. What is it that made the standard model work? You think about that. This incredible, beautiful, simple predictive theory. It's strange. It's this chirality, which is also some kind of ugliness in principle. When I call ugliness, I'm using some very funny aesthetical reasoning, which you should take as secondary. The beautiful theories of physics are those that are more predicting than the others, okay? The main beauty should come from our capacity to make predictions, rather than what is aesthetically appealing to us. You know, it works with just one Higgs doublet. Remember how it goes. This is a singlet, this is a doublet, and this craziness of the standard model, that it's also the source of, and it's everywhere protected. There is a beautiful essay by Weinberg, which actually was already 10 years ago. I couldn't believe it. V-A was the key when he was giving a talk on Sudarshan's birthday. Sudarshan is a great physicist, one of the fathers of the modern theory of weak interaction, the father of V-A. It's a mind-boggling story about Sudarshan, worth telling. Maybe I want to keep it tomorrow. I'll tell you a longer story, how he was twice robbed of Nobel Prize. And Weinberg says V-A was the key. Remember what I kept emphasizing V-A? Because now they could do a gauge theory, because you knew that there were vector and axial vector like current. And there was this complete asymmetry which works everywhere. Everything is so amazing, even protects this here. The same structure of the standard model protects theta bar. And then it fortunately fails for neutrino. I was just there visiting Texas, visiting Weinberg's group. Actually, Weinberg got the invitation. I was on my way to SUSY conference. And I gave a talk. My title was, Is Left-Right the Key? Is V the key? You know, claiming that the same beauty, fortunately, okay, but everywhere else, this crazy asymmetry, which I hope is wrong, works. It's completely self-protective. That cannot be, that we should appreciate. That's why it's such a great theory. Which of course sounds trivial, but it's a cliche to say. But I want you to, I'd like to repeat this greatness of the standard model, because when you go for talk, it's so easy to hear people saying that the standard model has problems. I'm already scared. In spite of what I say here, you will be writing thesis and I'll have to sit in the committee and I will hear diploma students, because their advisors, my colleagues, tell them that there is some problem in the standard model, so they write the thesis. Be careful, please. There is no problem in the standard model. Come to me, discuss with me, whatsoever. This is the problem. That's why we don't know, that's why we don't have, if there was a problem, there would be a new theory which we would be testing, okay? I have no idea which way to go. Since this is sort of, I was supposed to bring you up to the sort of prepare you for the summer school. So we can do the opposite. We can do the post-summer school. Think of the things that you heard, that you want to say. You can ask me, what about the dark matter and so on. So please ask me this question so that you can talk coherently to see whether they are a problem or not. Okay, prepare yourself. Ask any of these questions that you think are there. We can improvise we can also do that. Improvise a lecture on spot if it's interesting. Okay.